Okay, we're going to pick up where we left off on Friday with area versus volume, and of course do a little review of perimeter. So perimeter, area, and volume are your main computations that we're going to do in geometry class. And so I want to review the idea of the different dimensions that are involved. All right, so let's contrast perimeter versus area versus volume. It's important that we understand the difference between the two so we're not so dependent on memorization of formulas, and so we can explain the background of the formula to our students and we can make them see more concept. The procedure in finding area, volume, perimeter, these things is to use a formula. Substitute into your formula, find the answer. Memorize your perimeter formula. Well, that's elementary, lower level, when we don't have a quite understanding of what perimeter is, what volume is, what area is. So what we want to do is make sure you have an understanding of the three concepts and why area is what it is, why volume is what it is, why are units squared when we're doing area. And this has the idea of dimensions, okay? We're dealing with plane geometry and solid geometry. So before we go perimeter, area versus volume, we need to understand planes versus space. What is a plane? It's a two-dimensional what? Surface. Okay. What is space? It's three-dimensional. Okay, it is infinite in three dimensions, length, width, and height, whereas a plane is infinite in only length and width. So when we're doing these, we want to concentrate on dimensions. Okay, so this perimeter is one-dimensional, and we need to associate it with what? Let me fix perimeter, it's looking pretty bad there. Okay, so perimeter versus area versus volume. One-dimensional, two-dimensional, three-dimensional. What is the first dimension? And what word do we need to associate with perimeter? What's the first dimension? What would be? Distance. That's the word, but that's not the dimension. Length. Okay, length. And then we have distance. What is perimeter? The distance around a plane figure. And since this is only one-dimensional, it can be in a plane. So these two are plane geometry. This is solid geometry. It's not possible to have three dimensions on a plane. So what about area? What are the two dimensions associated with area? We're going to have length and width. Okay, so when we're dealing with perimeter, it's one-dimensional, it's length. Okay, it is infinite length, and this, of course, with a plane, with a line. Let's get rid of that. This is going to be a closed figure. And this, of course, is going to be a solid. All right, so perimeter is the distance around, and that's why our math computation is the sum of all the lengths. So perimeter. In Algebra 1, we're doing a little bit of analytic geometry, a little bit of finding the distance between 2 points on the XY coordinate plane, and using the distance formula, using the Pythagorean theorem. So I have a triangle on my XY coordinate plane, and I ask them to find the perimeter. Several of them did length times width. That tells me that even though they're in 9th grade, they never really got some of the basics of geometry concept. What is perimeter? It's always just the distance around. So all I do to find perimeter is sum the sides. It's one-dimensional. There really is no dimension. There is no computation here with the dimensions. I just add up all the sides. And that's why the units are in the first power, just regular units. Okay, so perimeter is a summation. Okay? And then area. What is area? Area is the product of two dimensions. Okay, I can't do the product here, I only have one dimension. So this is going to be the surface enclosed, because this is a simple closed plane figure, and it's going to be the product of two dimensions. So, and that's critical. It's not multiply the sides. It's not multiply the length times the width. It's not multiply the base times the height. We can summarize it down into multiplying or finding the product of the two dimensions. What is the key about dimensions versus sides? What's a dimension versus a side? What does a dimension have to be? Perpendicular, right? So this is going to be multiply two perpendiculars. So I'm not going to make the mistake of multiplying the length times the width on a parallelogram, because a parallelogram, the sides can be, they're not perpendicular. Okay, so what we've got here is area is two-dimensional. It has a length and a width. It is a simple closed plane figure. It's the surface enclosed by that plane figure. It's always going to be the product of two dimensions, meaning I have to multiply two perpendiculars. Whether or not they happen to be the side of the figure or not doesn't matter. That's why on a parallelogram, we cannot use what is kind of misnamed length and width. We have to use base and height, because to find the area enclosed by this plane figure, it has to be at perpendiculars. So kind of what we do is we actually are finding this area, which these happen to be equal, so it comes out to be the same. But it's only if we're working with perpendiculars. So area is always the product of two perpendiculars. And I showed you the other day that when we take a diagonal of a parallelogram or a diagonal of a rectangle, because a rectangle is a parallelogram, we divide our parallelogram or our rectangle into two congruent triangles, so then that derives the formula for the area of a triangle. Half of a parallelogram. So to find the area of our triangle, we cut our area of our parallelogram in half. What we want to do is we want to progress, especially if you're the teacher, you want to already be beyond the students in your understanding, so we're not requiring our students to memorize formulas by the time they're through 6th grade, 7th grade, 8th grade. All right, we want to take high school geometry. We want to prepare our students for high school geometry, and so we have to understand these concepts. Then we can concentrate on the proofs. Then we already are going to have an understanding of some of what the geometric shapes are and what these concepts are, so we don't have to do rote memorization in geometry class in 10th grade, okay? So we've got to get a basic understanding of area versus volume, and of course perimeter ahead of that. So all of my area formulas are going to be two-dimensional. Length times width, base times height. What about circle? Circles are two-dimensional. We have our little pi, which corrects for the fact that the circle doesn't have sides. Is that two-dimensional? Is that a product of two dimensions? Yes, the radius. That's why we have to square the radius. The circle can't really do summation of the sides, can we? But we have our pi, and then it's going to be pi times the diameter. Or if you have it in terms of radius, you're going to double the radius. All right, so is this a problem, mixing up these two? Sure it is. And it's a problem when we don't understand what we're doing. Circumference is comparable to perimeter, and so it's one-dimensional. See the formula? One dimension. One dimension. See the formula here? Area, how many dimensions? 2. If we're not dealing with 2 dimensions, it's not area. Okay, so area is always the product of 2 dimensions. Even if we're doing area of a circle, and perimeter is one-dimensional, even circumference is one-dimensional. It's the distance around our circle. Okay, do you see the difference? And do you see the stress on the dimensions? Because then volume is simply a step further than area. It's the product of what? 3 dimensions. Okay, and if we have this understanding of the concept behind, the principles behind, it unifies geometry. And that's what we want to do. We don't want to require memorization of all these unrelated formula here, formula there, formulas everywhere, right? So what we want to do is we want to have an understanding of the principle behind it. And the more you can show your students, the better off you're going to be. And the more they're going to not have to remember. So I don't have to tell my 9th graders, remember the formula for the perimeter of a triangle? No, I know what perimeter is. I know I need the area, I need to add up all the sides instead of trying to fish some formula out of my memory banks and picking the wrong one. Okay? There were several of them, and I had to write on their homework, this is not a rectangle, because they wanted to use a formula. So they fished P equals 2L plus 2W out of their brain and used it on everything. Okay, and these are 9th graders. And one of them was a boy. That usually doesn't happen, right? Okay, so do you get the idea here? So this is going to unify all of my area formulas, isn't it? What about everybody's favorite area formula, the area of a trapezoid? Do you remember the formula? You won't have to if you know what a trapezoid is and what area is. Here's my trapezoid. A trapezoid is also a quadrilateral, but can look like this. It has 2 bases, doesn't it? So what am I going to do? I'm going to average the 2 bases. Base 1, base 2. So the basic formula here is still going to be base times height, but I have 2 bases, so I'm going to average them. Base 1 plus base 2 divided by 2 times h. You may have seen this formula with a half in front of it, but that's the same concept. So to find the area of my trapezoid, I'm still doing base times height. Uh-oh. Which base do I use? Both of them. I average the 2. See how if I understand area, I can make sense of the formulas. And that's what I want to do. I want to make sense of the formula. Why is that the area formula for the trapezoid? Principles will always unify procedures. Okay, do you see the danger? And do you see the idea that when we are teaching just to copy the formula, plug the formula numbers in, solve the formula, there's our answer. That's rote procedure. Is that how you use a formula? Sure it is. Do you make them follow procedure? Sure you do. But what you want to do is strive to reach their understanding in 6th grade, 7th grade, 8th grade. Okay, 3rd and 4th grade, what's our goal for geometry? Teach them how to use formulas. But we're beyond 4th grade here. And we're starting to get beyond 5th grade here, so we want to get beyond how to use a formula. That's the first step. You remember our teaching progression? We start with terminology, then facts, then concept, then procedure. And do you remember first semester in just elementary mathematics? I said sometimes the procedure gets bumped ahead of the concept. That's 3rd and 4th grade. But now we've come full circle. From primary grades, we're working on basic concepts so that we can even do the procedures. Then in the middle, we're doing our procedures, and then now we're on the other end of the elementary spectrum, and we have got to come full circle back to the concepts. And if you're not teaching by concept, your teaching is going to be short term. Yes, you might finish your book. Yes, you might have good grades on their report card, but that's not an education. Okay, education is being able to be in 9th grade and doing higher level geometry and not constantly using the wrong formula. Okay, so we want to strive to reach the understanding with this. Then this will make your geometry work much easier, even on our test over this section. Do you understand what area is? Then you don't even really need the formulas. Okay, when I'm talking about a rectangle, even when I'm talking about my trapezoid, if I know what the trapezoid is, I can figure out its area with or without the formula, because I know area is always going to be the product of 2 dimensions. And so I've got my 2 dimensions. I'm not going to mess with the sides. They're not dimensions. They're not perpendicular. All right, then when I have let's see if we can draw a little better here. When I have a square, what's the area? The area is always the product of 2 dimensions. Oh, these are the same, so I'm just going to multiply them times themselves. I don't need to remember the side squared formula. I can use it if I want. Formulas are temporary for when we don't understand concept. Okay? We have a joke in 9th grade, formulas are for dummies. Okay? Formulas work when you don't understand concept. And I'm not saying you never use a formula. But if you understand underlying concepts, the formulas become less and less important. Okay? So I'm always going to do the product of 2 dimensions. If it's a rectangle, what am I going to do? I'm going to do the product of 2 dimensions, length and width. If it's a parallelogram, what am I going to do? I'm going to do the product of 2 dimensions. I am not doing sides, am I? You see the difference between perimeter and area? Because we've got to understand area, now I can move to volume. Okay? So what is volume? If we understand our area, that unifies all of our area formulas. Now let's go on to volume so we can understand and not have to memorize our volume formulas. Okay? So volume then is for solid geometry. It does not exist in plane geometry because solid figures have 3 dimensions. And then a solid, we have length, width, and height. Okay, so there's 2 things going on here. 2 ways we can approach volume. We can approach volume as a straightforward, let me do space here, that's the key. It's the space inside. So we have 3 dimensions, length, width, and height. Volume is the space inside a solid figure. Volume is the product of 3 dimensions. So we are going to multiply 3 perpendiculars. But better than that, another way that we can do, there's 2 ways. Here's where I want to show you that there's 2 ways to do the product of 3 dimensions. We can multiply 3 perpendiculars, or we can just multiply area by, I don't want to say additional, because we're not adding, but we can multiply then by a third factor, the height. Okay, look at this formula here. A equals capital BH. Again, it's time to reiterate that with formulas, capitals versus lowercase have significance. Capital A is area because it requires a computation. Little l, little b, little h, little w, those are lengths, they are lowercase. This is the volume formula. Sorry, not A. So V stands for volume because it takes a computation. And this is the idea. I can either do length, width, height. I can either do a straightforward multiplication of 3 dimensions, or I can take the area in 2 dimensions and multiply it by the 3rd dimension, height. This is going to unify even more volume formulas. And between the two of them, that's going to take care of all of our volume formulas. All right, so 1-dimensional, 2-dimensional, 3-dimensional. Here, there's nothing to multiply. We're just going to sum up our lengths. Here, we're going to multiply the 2 dimensions, the 2 perpendiculars. Here, we're going to multiply 3 dimensions. We can do it 2 ways. 3 factors in a row, or we can take the area of the base, the capital B, times the height. Okay? And this, of course, gives me units in 2 dimensions, and this gives me units in 3 dimensions. All right, so volume is just the next step after area. We're just going to multiply by a 3rd factor, the height. We're going to multiply by a 3rd dimension, the height. So let's spend some time on volume by itself. To do that, we need to go back, take a step back, and talk about solid figures. Three-dimensional figures. So solid figures. Solid figures involve 2 main, well, let's go ahead and get this set up. A circle is the set of all points in a plane equidistant from a given point. A sphere is the next step. A sphere is the set of all, same definition, the set of all points in space equidistant from a given point. Same definition, 2 dimensions, 3 dimensions. So this is the set of points in a plane equidistance from a given point. That equidistance is the radius. What about a sphere? Same definition, only it's in space. It's 3-dimension, 2-dimensional. So this also has a radius. That equidistance is still the radius, even though it's in 3 dimensions. So if we look at volume, this is section 12.4 in your textbook. This textbook approaches volume separately from area, and this textbook takes the multiply 3 dimensions approach, rather than the approach of just taking area 1 step further. Okay, so, but with this, how do we apply area versus volume to our sphere? How do we apply area versus volume to our sphere? How many dimensions do we have to have? This one is very straightforward. If I can find the area of a circle, I can find the volume of a sphere. It's one step further. This lends itself very much to the idea of let's take volume and let's teach it as the next step of area. Let's take volume and relate it to area. Let's take the sphere, which is three-dimensional, and relate it to the circle, which is two-dimensional. What's the formula for the volume of a sphere? Yes?
4/3 times.
4/3 what?
4/3 times.
What do we have to have? Pi? Mm-hmm.
Times radius cubed.
Yes. 3 dimensions. Okay? 4/3. 4/3. Okay? 4/3. With 4/3, the sphere, this is basically something that's going to have to be memorized. But it's still going to be, how many dimensions? 3. And it's a circle. It's still going to require multiplication by pi. What's the area? What's the area of a circle? It's two-dimensional. This is necessary to adjust for the fact that the sphere does not have the perpendicular dimensions, does it? No perpendiculars. And I'm not about to attempt to draw a sphere on the blackboard. Okay? So, volume of a sphere is still three-dimensional, even though because it's a sphere, because it's circular and does not have sides and doesn't have the straightforward perpendicular dimensions, we have to do the 4/3. Okay? So that is sphere versus circle. Then we have what are called polyhedrons. Okay, a polyhedron is kind of our three-dimensional equivalent for polygon. A polyhedron is a solid figure. It's a three-dimensional figure. It's a solid figure whose faces are polygons. Polyhedron is a solid figure whose faces are polyhedrons and whose edges are segments. Okay, when we look at a three-dimensional figure, the easiest one is a rectangular solid. Okay, our rectangular solid. Each of its faces, picture a three-dimensional box. Each of its faces are rectangles. Each of its edges are line segments. Each of its angles are at a vertex. So we have faces, edges, and vertices. This rectangular solid has how many faces? It's a box. 4 sides, a lid, and a bottom. 6 faces. Okay, how many edges? Well, we've got 4 edges. It's easy just to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? The 7th grade book has them do count the faces, count the vertices, count the edges. So polyhedron is a three-dimensional figure. It's a solid figure whose faces are polygons and edges are segments. So we have polyhedron. Basically, we're going to separate polyhedrons into 2 figures that we're going to deal with at this level. Pyramids and prisms. technically that rectangular solid is not called a rectangular solid, it's technically a rectangular prism. We can divide our polyhedron into two general shapes. A pyramid has one base, so its base, and then the three-dimensional point. So if it has one base, it's classified as a pyramid. This is a rectangular pyramid because its base is a rectangle. Pyramids are also a special type of cone. This would be a circular cone, right? Because its base is a circle. Then we have prisms. Prisms have two parallel and congruent bases. This rectangular solid has two rectangles as the base, the lid in the bottom. So this is actually more properly called a rectangular pyramid. We can also have triangular pyramids. A prism is typically a triangular prism, and that's why we call it that. Except with a triangular prism, the bases are two congruent triangles, okay? A circular prism, what do we call that? A cylinder. Okay, and when we're dealing with prisms, these are pretty much all that our textbook does is deals with prisms. We have a cylinder, which is a circular prism. We have a rectangular solid, which is a rectangular prism. We have a cube. And basically, a cube is a cube is a cube. Nobody calls it a square prism, though you could. You can even have a pentagonal prism, where the bases are two congruent pentagons. You can have a hexagonal prism, where the bases are two congruent hexagons. And when you look at volume with respect to prisms, then you can use this technique of volume being just the area of the base times the height. So this is usually where we begin with volume with upper elementary, is we restrict our volume to prisms. Because if we do a sphere, we have to memorize this number here, don't we? But if we do a prism, all we have to do on all prisms, whether it's a rectangular solid, whether it's a rectangular prism, rectangular solid, cylinder, or circular prism, all we have to do is find the area of the base and then take it times that height, that third dimension. So if you look in our volume section, all you're going to be working with is the rectangular prism or the rectangular solid. And if you think about it, what is the area? What is the area of a rectangle? Length times width, right? And then all we do is multiply it by the third dimension. That's how that formula is derived. So when we're dealing with the volume of prisms, we can deal with the fact that volume is simply another dimension. We're going to simply multiply by a third dimension. Volume is always the product of three dimensions. Okay, what about the cylinder? What about the cube? Well, we know the volume of a cube. All the dimensions are equal. So we just cube the edge, what the little e stands for. The volume of a cylinder. Because it's a prism, we can use this idea and we can take the area of its base, which is a circle, and then what do? Multiply by the third dimension. See, the volume of a cylinder is simply the area of a circle multiplied a third time by the height. See how that formula makes sense? And nothing to memorize. So when we first start doing volume and we limit to the volume of a cylinder, those are all technically prisms. All right, finding the volume of a pyramid and finding the volume of a cone is not something that we're going to do in elementary. Okay. All right, so you've got to take this a step further for the test, and you've got to understand area versus volume, and we'll throw the perimeter in there as well. So perimeter versus area versus volume. Make sure you understand that and can compare and contrast the two and do computations on basic plane figures and some basic geometric solids as well. Then before we leave area versus perimeter versus volume, we need to cover what are called composite figures. All right, so if you look at the handout that I gave you, what is a composite figure? Composite figures are used in upper elementary geometry to see if our students can put 2 and 2 together, which that in and of itself can be a problem. So what are composite figures? These are also found in the textbook. The textbook is when we take, a composite figure rather, is when we take 2 or more plane figures or 2 or more solid figures and combine them. We may add them together or we may take them apart. Typically in this section, the hardest section is the composite plane figures and the composite geometric solids. In your book on 12.4, Objective B is finding the volume of composite geometric solids. So what you have to do is you have to look at the figure and see, is this the sum of 2 figures or is it the difference of 2 figures? The You Try It problems on 549, we have a geometric solid. Example 5, you can see we've got a rectangular solid plus a little cylinder on top. Or example 6, we have a rectangular solid with a cylinder cut out of it. So when we're dealing with composite figures, we will have to do the computations separately and then either add them together if they're put together or subtract them. On the handout that I gave you, you can see we have what looks like a hockey rink or something, and I'm asking you for the area and the perimeter of those composites. The first one, we've got a rectangle with a triangle cut out of it. I want both the area and the perimeter. The composite is going to show me that you understand the difference. So if we take a composite figure, let's do plane figures first. Maybe I'll have something like this. And I want the area that's shaded. I will have to give you the radius, and I will have to give you the length and the width. Or if this is a square, I'll have to give you the sides. The perimeter here is just still going to be, what, 20 centimeters, irregardless of the circle I cut out of it. But what is the area? That's a composite figure. We have to look at it. Okay, I want the area of this shaded figure. So I'm going to have to find the area of the square, subtract the area of the circle inside. So this is a way to make sure you do this worksheet, and this is a way to make sure that you understand area versus perimeter versus volume. I might have a rectangle with a square cut out of it. Whoops. So I don't want this, I want this. Shaded here, I'll take this. The easiest way to do this would be to find the area of the whole rectangle, then find the area of the square and subtract it. What else could you do? You could cut this into two rectangles and find this area and add it. It's just a matter of what you prefer to do. But this shows me that you can do area computations. What is the perimeter? The perimeter is not going to be this whole thing. These sides are not there, and these sides are. If it is a rectangle and a square, we're going to end up with the same, because this side is equal to this side, and this side is equal to that side. But we have to sum the sides. A lot of times it can be a problem when we have a rectangle and then we cut a circle out of it. But this isn't a whole circle, is it? It's a half of a circle. So here's a composite figure where you have to take the area of the rectangle and subtract half a circle's area from it. So it's just a matter of using the formulas and showing that you understand them, which is done a lot with 7th graders and 8th graders in their geometry section. But you guys are not 7th and 8th graders, so I'm not going through how to do each one. What do you have to do with a 7th grader? You have to address the composite figures specifically. You must address them specifically. You must show them what a composite figure is. And you must stress to them, I erased it, but you must stress to them that the dotted lines are not there. You must stress to them that's only half a circle, and you have to work through them together and help them acquire the thinking skills necessary for putting 2 and 2 together, for putting 2 figures together, for understanding perimeter versus area. So composite figures will be a part of your test. And which is why I want you to do that handout, because I want you to be prepared for that. So let's finish this section with a little bit of trigonometry. So then tomorrow what we will do is I will go over teaching the trigonometry, and then we will take the test. But let's go over doing the trigonometry in 12.5 and 12.6. What is trigonometry? It's the study of triangles, the measurement, literally the measurement of triangles. So we should know some things about triangles. We should be able to find the perimeter of a triangle, basically without thinking about it. All right, we should be able to find the area of a triangle without thinking about it. And then we can transition to what's called right triangle trigonometry. With right triangle trigonometry, we can do a lot of application problems, because many times we can divide a geometric shape into right triangles. This is used for the distance formula between 2 points. We can construct right triangles and find missing sides using the Pythagorean theorem. The Pythagorean theorem is based on a specific setup for my right triangle. By convention, when we use the letters A, B, and C as the vertices, we put C at the right angle. Also, it's proper to label the opposite side with a lowercase. So with this right triangle. The right angle is C, so the side opposite is labeled little c. It's called the hypotenuse because it's going to be an important side. It's always going to be the longer side of the three, and it's the basis of the Pythagorean theorem. The two other sides are called legs. And the Pythagorean theorem tells us that the square of the hypotenuse is always equal to the sum of the square of the two legs. Rather than always saying other sides, we call them legs. So that's the Pythagorean theorem. And since that's a formula, we can solve for missing hypotenuse. We can solve for a missing leg, depending on what is given. So many times with an application problem, maybe we're dealing with some type of tower, and we know we have a cable attached to that tower. Well, theoretically, the tower should be at right angles with the ground. Let's say we know how high the cable is here and how far the cable is here, and we need to know how long the cable is. Are we going to climb up the tower and shoot a tape measure down? No, we're going to use the Pythagorean theorem. What if we need to know the distance across the lake on campus? What are we going to do? Get a really long tape measure and paddle across? No, we're going to make a right triangle and we're going to use trigonometric functions. Okay? We can even do triangles that aren't right triangles. We can do trigonometric functions on those. You're familiar with sine, cosine, and tangent. That's all a part of triangle measurements, the so-called branch of trigonometry. Okay, so when we're dealing with the Pythagorean theorem, the first step is to understand the setup and the labeling of the triangle and what we're dealing with the hypotenuse. Okay, and then it's going to be used to find missing sides of triangles. It's going to be used in application problems on 12.5. So 12.5, getting at the very end of your textbook, page 555, will be first of all learning how to just use the Pythagorean theorem. All right, and this was based on the area of a square and dividing it into two halves. But we're not going to go through the derivation of it. We're going to begin with just using the Pythagorean theorem. What's the problem with using the Pythagorean theorem in 5th grade? We're not going to use it. Why not? We're going to start using it a little bit maybe in 6th grade, but mostly in 7th and 8th grade. What's the problem with it? To solve, what additional step do we have to do to solve for C? Yes? Square root. Okay, so a lot of times you'll see the formula in this form, solved for C. So the first thing that we have to do is we have to learn how to handle the square root. And you can see in the book they've given you the idea, they've given you a list of perfect squares and so forth. So the Pythagorean theorem involves taking the square root. So we have the potential for quite a bit of irrational numbers, because most square roots are irrational. So that requires that we learn how to we recognize, first of all, the perfect squares. It'll be very handy for you to know the perfect squares 1 through 20, especially some of the oddball ones. Your students are going to know the perfect squares through 12, aren't they? Maybe 13, 14, and 15 if they learn the 13, 14, and 15 times tables like we teach our 5th and 6th graders. But then we have the square root of 16, 17, 18, 19, and 20. So it'd be a good idea for you as a teacher to go a little further than the times tables. 169. What's the square root of 169? 13. So if we just go a little further here, 13 squared is 169. That will crop up a lot. You want to be familiar with it. This one I remember by just being a little dyslexic and making it 196. What's 15 squared? 225. 16 squared? 256. 17. 289. 18. What does it have to end in? It has to end in a 4, so it's 324. Sounds good to you guys? Right? 64. Is that right? Okay. 19. I have trouble remembering this one. I should have written it down. I didn't. What is 19 squared? It's got to end in 1. What's 20 squared? 1. So this has got to end in 1 and be less than 400. So I'm guessing 381? No. 361? 361. 361. It's 361. Check it on your computer, but I'm pretty sure it's 361. All right, so 20 squared is 400. And so before we're going to teach this in 7th grade, we have to go through squares and square rooting. And we have to first recognize and understand what a perfect square is, and then recognize kind of our upper perfect squares. We will also have to allow, is that correct? Yeah. Okay. We will also have to allow them to use a calculator on application problems so that they can, in my opinion, when we're doing just regular sides of triangles, we should leave the answer irrational. Square root of 13, square root of 17, square root of 10, square root of 42, okay? But on application problems, we should tell them where to round their decimal approximation and require them to use a what? Unit. Just because we're square rooting and just because we're using the Pythagorean theorem does not allow us to ignore units. So what we're going to do is set up right triangles and use the Pythagorean theorem. So when you do 12.5, you can see they're wanting you to use a calculator. That's fine. Just go ahead and go through the practice of it. Make sure on this case that since these are geometric shapes and these geometric shapes all have units, to me the key to understanding how to express your answer is whether or not they're units. When there's a unit, you need to give a decimal approximation. And the book tells you to go to the 1,000th place. See that? So follow their directions. And then with the application, this book is pretty good about that. It is going to tell you where to round. You're going to set up a right triangle. You're going to identify which side would be the hypotenuse, which sides would be the legs, and solve using the Pythagorean theorem. You can see we've got an L-shaped sidewalk we can make a right triangle out of. We've got a ramp that's a right triangle. We have a ladder propped up against the side of a building. All of these are used as application problems. We construct kind of an imaginary right triangle and solve the missing side. And then 12.6, we've already mentioned similar versus congruent. And several of you on the quiz did not use a key word with similar and congruent. Anybody know what that key word is? Maybe I didn't stress it enough, but we learned it with 2 parallel lines cut by a transversal. What's the key word with, other than the obvious vertical angles and supplementary angles and the equal angles with respect to the lines, we also had a new kind of equal angle with respect to having 2 lines and 2 different figures. They were called corresponding angles, right? So when you're dealing with both congruent and similar, you have to deal with corresponding parts. And of course with geometric figures, plane figures, we're dealing with angles and sides. So if the 2 figures are congruent, we have to relate the two figures, and we have to say that the corresponding parts are equal. Corresponding angles are equal, corresponding sides are equal. That's for congruent. Corresponding parts, both, are equal. They're the same size, so the sides have to be, the corresponding sides have to be equal. They're the same shape, so the corresponding angles have to be equal. Key is the word corresponding. Otherwise it's too vague. Similar. Similar, we're just mostly doing triangles. Similar triangles, the corresponding angles are equal, but the corresponding sides are in what? Proportion. So when we're dealing with similar triangles, we have to set up a consistent proportion. So when we're setting up our proportions, we have to have a given proportion between figure A, let's say, the first triangle, and figure B, the second triangle. We have to have the proportion of triangle to triangle. Then in the second ratio of our proportion, we will have the missing corresponding side. And I use the word consistent proportion. So I have to compare triangle to triangle in order, and then corresponding side on the first triangle to the corresponding side on the second triangle. Okay, that's the key with proportions, is setting up a consistent comparison. By definition, what is a proportion? Two equal ratios. So if I invert or mess up the order of my ratio, my proportion will not be equivalent, and I will not be able to solve for the missing side. So congruent, see, is pretty easy. We go with corresponding parts being equal. We mentioned the other day some geometry theorems on page 562. The side rule, and they just give you the first two, the main two, the side angle side rule. If you can show that all the sides are equal, that's kind of obvious, you can say the triangles are congruent. Or if you can show that the two sides with the included angle are equal, you can prove the triangles are congruent, both equal sides and equal angles, but we're dealing with equal corresponding angles, equal corresponding sides. Okay, and then all of these can be used for finding missing sides.